Hi, I'm Mark Barsamian. In this video, I'll be discussing an important mathematical constant called e, and discussing the exponential function e to the x. The reading for this video is from section 3.1 of the book, and more specifically, just page 181. The corresponding homework is this pair of two problems from section 3.1. I think only one of these is in my lab. So I want to talk about the constant e. We're going to start by talking about this limit. Do we have any intuition about whether this limit exists and what might be its value? Well, notice two things about the limit. First of all, the thing in parentheses will always be greater than 1, because if n is a positive number, and it is because we're imagining n going to infinity, so n will be positive, so 1 over n will be positive. And so what we have in parentheses is 1 plus something that's positive, and so the thing that's in parentheses will be positive. Now, recall that when a number greater than 1 gets raised to higher and higher powers, the result gets more and more positive without bound. So for instance, if you take the number 2 and you raise the number 2 to the third power, you get 8. If you raise the number 2 to the fourth power, you get 16. You raise the number 2 to the seventh power, you get 128, and so on. So based on that observation, it could be that maybe this limit will turn out to be infinity, because it could be that this thing gets more and more positive without bound when n gets more and more positive without bound, based on this kind of observation. On the other hand, notice that the thing in the parentheses is getting closer and closer to 1, because 1 over n is getting closer and closer to 0. That is, let's go back up and look at that. N is getting huge and positive, so 1 over n will be a very, very small number. When n is 1,000, 1 over n will be 1 over 1,000. That's a very small number, very close to 0. When n is 1,000,000, 1 over n will be 1 over 1,000,000, very close to 0. So the thing in parentheses is getting very close to the value 1. Now we know that 1 raised to any power is just 1. So 1 cubed is 1. 1 to the fifth is 1. 1 to the seventh is 1. So based on that observation, we might wonder if maybe the limit will turn out to just be the number 1. Because again, the thing in parentheses is getting closer and closer to the number 1, and when you raise 1 to any power, you get 1. So it would be believable if it turns out that the limit is infinity. It would also be believable if the limit were to turn out to be the number 1. Or maybe the limit will turn out to be not infinity and not 1, but maybe some other real number. So to figure this out, let's explore some values of this quantity as n goes to infinity and see if we can see a pattern emerge. So we'll make a table of values. For these values of n, notice those are getting more and more positive without bound. We'll compute values of this. Well, so when n equals 10, this expression becomes the following. Now, how do we compute something like that? Well, let's get a calculator up. Let's go to the website called Wolfram Alpha, and let's type in that expression. So we see that the decimal approximation for the quantity 1 plus 1 over 10 raised to the 10th power is roughly 2.594. Now what about when n equals 100? If I type that expression into Wolfram, I get the following. I get roughly 2.705. And if I continue in this way, for n equals 1,000, I get roughly 2.717. For n equals 10,000, I get roughly 2.718, and so on. Notice that we can describe these trends using symbols. We would describe the trend in the value of n as n is going to infinity. So based on what we see in this table, it seems like maybe the limit does exist, and maybe it's a number near 2.718. Now, we haven't proven that the limit exists, and we haven't proven the value of the limit, but it seems like it probably does exist, and its value is probably near 2.718. Now, in your homework, you'll be constructing a table like this. You will have to give more digits here. You'll have to give 5 digits. So you'll have to do work like what I did, but you'll have to write down more digits. Well, so this limit is famous. It's a big fact from higher math that the limit does exist. And the symbol e is used to denote the real number. That's the value of the limit. That is, this limit is e. So the limit is not infinity. It's a real number e. And the number e is between 2 and 3. And it's near 2.718, but the number is what's called irrational. The number e cannot be written exactly as a fraction or as a terminating decimal or even as a repeating decimal. It's irrational. And that number e is called Euler's number. Now think about this related limit. This limit has an x inside. It turns out that if you do a change of variables, you can show that if the previous limit was the number e, this limit with the x inside turns out to be e raised to the x power. So this is a function, and it's called the natural exponential function. Now, when I write functions, I like to put parentheses around the x in the formulas for the functions. So I'll write it in a way that has parentheses around the x, and I'll give it an official introduction. So it's the natural exponential function, and it's defined by this equation. Now I want to turn our attention to the graphs of this function and other functions like it. So the strange or surprising way that we arrived at that function we can forget about for now, but we can just turn our attention to its behavior. So more generally, if you have b a real number such that b is between 0 and 1 or b is greater than 1, then the function b raised to the x power is called the exponential function with base b, or the base b exponential function. Now the most common exponential functions are e to the x, the one that we just saw, 2 to the x, and 10 to the x. It'll help our understanding of these functions if we review how their graphs are constructed and then study the graphs. So we're going to build the graphs for 3 exponential functions, these 3. 2 to the x, 3 to the x, and e to the x. So I'm going to make a table of values for those functions. We'll start with 2 to the x in this column. We'll do the easiest entries first. So when x is 1, 2 to the 1 is 2. When x is 2, we get 4. And when x is 3, we get 8. Another easy one is when x is 0. Now, the values when x is negative, we have to think about for a bit. Here we used a rule of exponents. The rule of exponents says b to the minus p power is equal to 1 over b to the p power. So when I want to compute 2 to the minus 1 power, it's just simply 1 over 2 to the 1 power. So in other words, 1/2. We'll do similar computations for x equals minus 2 and minus 3. So there's the table of data for 2 to the x. Let's skip over and do the table of data for 3 to the x. I'm going to go quickly here, similar computations. So there's our data for 3 to the x. How do we do e to the x? We have a decimal approximation for e. E is roughly 2.718. But I just want to use the information that e is between 2 and 3. So that means that in this middle column, the numbers are always going to be between the blue and the green numbers, the values. So let's just write this symbol for the numbers in the middle column. So there are the symbols for the values of e to the x. Those symbols are the only way to write the numbers exactly. We can't express these numbers exactly using decimal approximations because the number e is irrational. Now let's graph these values. So let's start by graphing 2 to the x. So there's a very crudely drawn graph of y equals 2 to the x. Now let's put on the data for the green graph, y equals 3 to the x. So you see that the graph of y equals 3 to the x goes up very quickly on the right side. It goes off scale. It's above the graph of y equals 2 to the x on the right side. But on the left side, the graph of y equals 3 to the x actually is underneath the other graph. Now, what about the graph of y equals e to the x? Well, go back up and look at our table of data. What we observed about the data for e to the x is that because e is between 2 and 3, the values of e to the x are always going to be between the values of 2 to the x and 3 to the x. So let's go down and just draw in a red graph that sort of shoots between the blue and green ones. So this graph would have 0.01 and 1 comma e, which is between 1 comma 2 and 1 comma 3. It would have the point 2 comma e squared, whose y value is between 4 and 9. And it would have this point over here, negative 1 comma 1 over e, which is between negative 1 comma 1/3 and negative 1 comma 1/2. So this graph is not meant to be drawn to scale, but it's just meant to show the relationship between these graphs. On the next page, we'll look at a computer-drawn graph. Here's a computer-drawn graph of those same equations, those same functions. So you can see that I can only include the interval from negative 2 to 2 before the graphs really go off scale. Oh, it looks like I've made a mistake here. This should be the point 0 comma 1. Now let's think about some common behavior of all these graphs. First of all, some easily recognizable points. For one thing, all the graphs go through 0 comma 1. That's because b to the 0 power is the number 1. In our table, all 3 of those columns had a y value of 1. The next thing to observe is that all 3 of these graphs go through a point of the form 1 comma b. That's because, let's go back up and look at our table, b to the 1 is just b. Another easily recognizable point is this one, negative 1 comma 1/2, negative 1 comma 1/3. Those points are all of the form negative 1 comma 1 over b. Let's go up and look at our table of data. When x is negative 1, b to the x is b to the negative 1, which is just 1 over b. So that's one bit of common behavior of those graphs, the 3 recognizable points. Another bit of common behavior is the domain. Notice that the domain is all x values. No matter what value of x you use, you get a y value. So the domain is all real numbers x. Now, what about the range? What kind of y values do you get? Well, on this graph, it seems like all of the y values live above the x-axis. Let's go back up and look at our calculations. Sure enough, whenever I compute my y values, I either have a number that's greater than or equal to 1, or I'm taking 1 over a number that's greater than or equal to 1. When I take 1 over a number that's greater than or equal to 1, I get a number between 0 and 1, but I'll never get 0 because I have a fraction with a 1 on top. And I'll never get a negative number because I'm taking 1 over a positive number. So it makes sense that the range is all y greater than 0. Let's notice some other things. All these graphs go up on the right side, and all of these graphs have a horizontal asymptote on the left side. And also, all these graphs, as you go from left to right, the graph goes up. So let's put all these observations in a box. So I discussed the domain and range. The domain is the set of all real numbers. In interval notation, that would be denoted negative infinity to infinity. And the range is all positive y values. And in interval notation, that would be denoted parentheses 0, infinity. The 3 distinctive points, the point 0, 1, the point 1, b, the point negative 1, 1 over b. The end behavior. The graphs go up on the right. Well, in terms of limits, we would write this. The limit as x goes to infinity of b to the x is infinity. And the end behavior on the left side, the graphs have horizontal asymptotes on the left with line equation y equals 0. So expressed in limit terminology, we would say this. The limit as x goes to negative infinity of b to the x is 0. And finally, I mentioned that the graphs are all increasing as you go from left to right. So if you go from left to right on the x-axis, then the y values go up. Now these are exponential functions with base b that is greater than 1. We had 2 to the x, e to the x, and 3 to the x, but in general, this would happen for any exponential function where the base b was greater than 1. That's the end of the video. Thank you.